this is how they look like. These are the thermal probes which we developed, and these are the thermocouples which were used for measuring how heat migrates in the geomaterials at different distances and different times. This was the work which was done by my students Gangadhar Rao, David, Dr. Dali Naidu, who is a faculty member now at IIT Chennai, and later on Hanumant Rao and Shrideep, and a lot of people use these gadgets. They appear to be very simple, but when we were devising them, I am sure you must have realized that it was a tough time and we were not having much knowledge about how to fabricate these setups. So, this is the setup which was developed by my student David. This is the field thermal probe which is 1 meter long, and this was the master's student thesis. And what we did is we divided the entire probe in 3 sections, and these 3 sections the temperature was monitored by using 3 thermocouples. We call them as the top, middle and bottom. The beauty of this system is that you can do thermal profiling of the ground up to 1 meter, and if you want to go deeper, then you can cut a trench and you can do first profiling 1 meter, again you can do 1 meter, and then you can keep on doing as long as the system permits. So, we apply a constant power through a constant power supply device. We heat up the nichrome wire, the concept remains same of the laboratory thermal probe and the field thermal probe, and when the heater emits the heat and when the heat gets equilibrated in the soil mass, we measure the temperatures by using 3 thermocouples. Alright. So, this becomes a thermal probe. Now, in the process we also developed different types of devices which have been used for determination of thermal property. They are all in-house development. So, what you see here is the CBR mold or a Proctor compaction mold, and then the thermal probe which was developed can be inserted into the compacted soil mass with the help of a dummy rod. So, the diameter of the dummy rod is slightly less than the diameter of the thermal probe, and it is to ensure minimum disturbance which is caused to the soil when you insert the thermal probe. This is the field thermal probe which I was talking about. This is the setup, constant power supply which heats the nichrome wire in the thermal probe. Thermocouples reading are displayed on a temperature reader, and this is the mold which was used for creating the soil samples under control conditions and calibrating the thermal probe. It is a very interesting device which we developed, is known as thermodet, and the name came from thermal property detector. Alright, so we named it as thermodet, and what you are observing is this is a stainless steel hollow cylindrical tube, and there is a cap at the bottom and there is a cap at the top which a hole, and through this hole the thermal probe can be fitted. After compacting the sample in this thermodet device, we can put this collar or the cap at the top, and then we can insert the thermal probe through it. Later on, this device can be either kept in an oven, and I can find out how the heat migration takes place from outer periphery to the inner periphery. After attaining a certain temperature, I can take out this device and I can put it in a water bath also, and then I can observe how the cooling of the soil mass takes place. So, in this way the heating and cooling cycles of the geomaterials can be studied. The results which we obtained from these type of tests were utilized to create a software which is known as DD Therm, and I did a lot of consulting by using these tools as well as this software, and that became a big source of earning. There was a time when we used to supply these thermal probes to different western countries also, particularly the power plants, those who were quite eager to know the thermal properties of the soil mass before the trenching operation takes place. So, a little bit about this transient method. So, basically the probes which I have shown you act as a line heat source. These are like pen. So, truly speaking, this is a line heat source and the heat is getting emitted in the radial direction. Alright. So, we call them as a line heat source. That means the heat source happens to be a line, and this is how it looks like. So, if you take some soil sample in the mold, this is the thermal probe which is fitting at the center, and then I have fitted the thermocouples which I have shown at different radial distances and different z's of the sample. So, the basic idea is to measure the heat migration in the radial direction. This is a typical axisymmetric problem where the symmetry of thermal regime is along this axis, and what we want to do is we want to say, or we want to find out what is the temperature in the soil mass because of its heating as a function of r and t, radial distance and time. So, this is the equation you remember, which is the second order differential equation, fine, and this can be utilized for finding out the pore water pressure, 3-dimensional consolidation, or the thermal diffusivity. So, theta is the temperature, rate of change of temperature with respect to time is thermal diffusivity. Second derivative of rate of temperature change with radial distance 1 upon r into del theta by del r. Similar equation is for 3D consolidation also, if you remember. So, then we can substitute boundary conditions, and we can get this expression, Q is the power supply, which is I square into R. R is the resistance per unit length of the heater wire which has been fixed inside, and then if you solve this expression, this is the function which you get. I hope you remember this function is Euler's constant. So, ultimately this equation yields delta theta is equal to Q upon 4 pi K. K is the thermal conductivity, inverse of thermal resistivity. Can you recognize this term? Somewhere you have seen this in your conventional geomechanics. What is time factor? CVT upon d square, alright. So, truly speaking, this is 4t alpha u equal to r square, clear. So, this is sort of a function which is nothing but your time factor, which you will be getting when you solve this expression. So, r is the distance of the heat front, t is the time, alpha is the thermal diffusivity. So, if I do these experiments and if I use this expression, I can easily obtain the thermal diffusivity, and by solving this equation I can also get change in temperature. If I know the value of Q, which is I square R, I can obtain thermal resistivity. So, out of the 3 parameters I get 2 parameters by conducting this test. Now, how would you interpret it? The interpretation is like this. I can plot temperature versus time in 2 ways. One on a normal scale and second one is on the log of time scale. So, this is the equation which I have to solve. So, basically this is delta theta upon log of T2 by T1, which is the slope of the line. So, having conducted the experiments, if I plot the results and if I get the slope of the theta versus time profile or the graph, I know the slope, which I can substitute over here, divided by Q upon 4 pi, and you get thermal resistivity. Once you get thermal resistivity, inverse of this will be thermal conductivity, and wherever this line cuts the x axis, that T value becomes T naught, and what I can do is I can substitute it over here. R is known, T is known, I can obtain the function u, and hence I can obtain the alpha value. So, which is the thermal diffusivity. So, that means we have obtained RT and thermal diffusivity, and then you can obtain the Cp value. Is this part okay? So, when I started my experiments on thermal properties of soil, I never realized that what will be the scope of application of this type of studies. But in today's world, I am realizing that these properties and these type of experiments have become so important, and their applications are so diverse that sky is the limit. One of my students, Dr. Krishnaya, he applied all these concepts to determine the quality of the food grains, rice, wheat, sugar, and how to stop the germination, because germination of the grains is a function of temperature and humidity. Now, he was the guy who extended all these concepts to find out the condition of the packed meat and the fish, because as these items rot, they disintegrate and their thermal properties change. So, that is when I am saying the sky is the limit to think about the application of these parameters. So, Dr. Krishnaya did a lot of work in this area, and we also extended these concepts to determine the thermal properties of concrete and different type of composites. So, these are the details of the thermodet, which was designed by my student David. I explained this also. This is a hollow tube in which you can fill up the geomaterial, and the bottom portion is an insulator. Top cap is also an insulator, and through which the thermal probe can be inserted into the geomaterial, and then I can do heating and cooling experiments. All this is published work, so you can find it out from the literature, and there is nothing new for that matter, but now these tools have become very useful for solving various problems which geotechnical engineers are facing. Typical cooling curve. I hope you can realize that the temperature is dropping down as the time increases. The previous one was the heating curve. So, here if you see, as the time increases, the temperature of the soil mass increases. So, this is a typical cooling curve, where after heating the sample in the oven, you take it out and put it in a water bath. So, I can get the properties of geomaterials, thermal properties of geomaterials, both under heating and cooling cycles, and then I can use them for various industrial applications. Some more similarity between the consolidation studies which you do and the heat experiments which we are doing. If I define a term as percentage increase in temperature of the soil mass, and this is the time factor T, which corresponds to 50% change in the temperature. So, this equation is well known to you, alright. So, corresponding to T 50% change is somewhere here. So, if I go in the horizontal direction, wherever this cuts these graphs are nothing but the solutions of the Euler's equation which I showed you, the time series for different geometries of the mold when the height is quite long. The second solution is when height is 2 times the diameter of the mold. So, for 50% mu value you can get capital T, you can substitute it over here and you can get diffusivity. I mean, these devices are now quite commonly used, and you can read about them in the published literature. These results show you the effect of different soils which are listed like WC, SS, black cotton soil, and weathered soil as a function of density and RT. So, the first thing which I wanted to show you is that thermal resistivity is inversely proportional to gamma D, and the logic I gave you, the better contact between the grains, for better gamma Ds, the resistivities are going to be less. So, because higher gamma D corresponds to lesser air content in the voids, and hence the resistivities are going to be less. Another way of interpreting this would be if you plot RT with respect to moisture. So, this is how the peculiar curves look like. They all tend to converge at a certain point. So, if you keep on adding moisture to the soil, say about more than 40 or 50%, what is going to happen? All of them will converge to a point which will be the thermal resistivity of the water. So, this type of analysis shows that thermal resistivity of water is less as compared to thermal resistivity of the soils and the air. And this is where you can see the influence of the gamma D also. The lesser density shows more resistivity as compared to higher density. So, higher density indicates lesser resistivity and more moisture indicates lesser resistivity. Clear? So, these things are quite easily understandable, and they can be used for designing various thermoactive structures. Now, if you plot the thermal diffusivity as a function of gamma D, what we observed is that this remains unaltered. There is no influence of unit weight on the thermal diffusivity. Similarly, if you plot thermal diffusivity with respect to moisture content, we observed some changes, and this is where the effect of gamma D gets translated. A denser system will show higher diffusivity as compared to a lighter system. This is quite understandable. Later on, my students like Dr. Padma Kumar and Somnath Mandal and Sanyam Dangayach, they all did modeling of heat migration through the continuum, where you have used these concepts of how diffusivity and resistivity parameters can be linked with discrete elements or finite elements to show the migration of the heat in the continuum, which is geomaterials. Of course, the last parameter is the Cp, that is the specific heat. When you plot it with respect to gamma D, again there is no variation, but when Cp is plotted with respect to the moisture content, there are few trends which are appreciable, that as the moisture content increases, the specific heat of the material increases, and that again is because of the water, because water has a very high specific heat capacity. So, these type of studies were done, intensive experiments were done based on the gadgets which I showed you, and then what we did is we created generalized relationships for professionals to use them. These generalized relationships were known as DD Therm, which I said, and they were developed and proposed by my student David for single phase system, for moist soils, and we have different coefficients which are coming over here. You need not to write it down, all this is published work, you can check it from the net. So, these are the coefficients A, B and C, which would depend upon the type of the soil which is being used, that is the is matrix or the what we call it as the texture. So, you have to do the particle size analysis first, and then A, B and C will depend upon how much clay fraction, silt fraction, fine silt, coarse silt, sand, gravels the soil has, and then you can superimpose all these things over here. And then we came out with some guidelines also how to obtain A, B and C parameters depending upon the moisture content and type of the soil. So, as you can observe, the parameter A depends upon the fraction of the particle size, B largely depends upon moisture content as well as the particle size, and C parameter again depends upon the moisture content and the particle size. So, put together all these things, you can use them, and this software is already there. Using this software, I did a lot of consulting work for Boeing, Hyundai, different types of thermal power plants, and different types of solar ponds which are being constructed in the country, foundations for the furnaces and the forging units. So, these are the applications where thermal properties are being used, and of course, the cable laying process where most of the industries which are dealing with the cable laying operations would like to obtain the thermal properties so that they can design the configuration of the cable.
So if in a furnace, sir, the temperature at the surface, like the concrete floor, goes very high, then if there is underlying fine grained soils, then there are like large chances of settlement because of the drying
Cracking,
out of the water.
First of all, cracking itself.
Cracking of the floor will take place if the underlying water content gets lost in the fine grained soils. So, like, how would you prevent it? You treat it, or like
you have to design thermal barriers. So, if you are so eager to know about this, you should read the papers published by Dr. Cole, where we have designed FTBs, fluidized thermal beds. So, these FTBs are laid in the foundation of the trenches, fluidized thermal beds, FTBs. So, these type of systems are designed and they are provided in the foundations of the structure so that the heat which is generated from the structure gets easily dissipated in the soil mass. So, this is the engineering of the soil mass which you have to do based on its thermal property augmentation. Are you getting this point? Yes.
that is the question. Since you are like allowing the heat to go into the soil mass, if it is a fine grained soil mass, let us say, then like your whole slab downward portion can sink the soil below the your concrete floor. If it's not a slab simple, then if it's a if it's not a raft, then there might be cracks in the floor itself, sir.
Correct, you are right. So, your questions are interlinked. What heat flux does? It changes the moisture content in the soil mass. Fine, it initiates the drying process. This is what is known as coupled process. That means the heat front is moving in the system, and along with it, it is taking out the moisture also along with it. So, this becomes a coupled phenomena, migration of heat and migration of moisture. Subsequently, we will observe that once the migration of moisture takes place from the soil, the tensile strength mobilizes, clear, and if the tensile strength is lesser than the thermal stresses, the material will crack. Fine, this is number one. Number two, fine grained soils with active minerals, where their tendency is to absorb and desorb moisture, clear, we call them as shrinking and swelling and shrinking phenomena. So, this type of an action might get actuated because of thermal flux migrating through the soil mass. So, where the engineering? The engineering is create the barriers in such a manner that this transition becomes as less as possible, as less abrupt as possible. So, what I have done, delta theta divided by L, which was extremely high, I can design a filter in such a manner that delta theta upon L can be negotiated to become a very small number. That is it. And that would depend upon the properties of the material which I have used in the filter bed, thermal filter bed, clear, or thermal dissipator. So, this acts like a shock absorber, so thermal shock absorber. So, that is what has to be designed. Hope you are realizing the intricacies associated with this. So, next time whenever you see any trenching operation where the cabling is to be done, just stand by the side for some time and see how do they do it. So, there is a special procedure which is to be adopted for laying the pipelines. So, sorry, for laying the thermoactive pipelines and the power cables. You cannot just lay them on the ground. Second implication of all this discussion could be, because of thermal heat migration, there could be an expansion in the pore fluids, because we are talking about thermal expansion coefficient of the fluids, which is air and the water. So, imagine a system which is control volume and you are applying thermal flux. So, what is going to happen? Pore pressures might develop. So, thermal consolidation is the term which comes handy in defining the system's ability to not to create or develop the pore water pressures inside this because of thermal loading. So, now the whole context gets changed, rather than the mechanical consolidation, we talk about thermal consolidation. Are you realizing how the things change? And this is the work which was done by Rakshit, and all of you attended his PhD defense. He was talking about thermal consolidation, if you remember. And before that, one of my master's student, Puneet, he did some experiments on thermal consolidation of geomaterials, and he has filed a patent also for a setup which he has developed himself to study the thermal consolidation in fine grained material.
Like what I have got is, if there is fine grained soil, above that I have to use some special type of geomaterial in which I can use them to diffuse the large temperature variations.
Rather than doing all these things, the best thing would be, when you go to cold climates, what do you do?
Cold climates.
Huh? Yes, wrap your body with an insulator. Clear? Here what we have to do? We have to wrap the entire utility with a conductor. The moment you wrap it with an insulator, what is going to happen? The temperatures will build up inside. This is a reverse philosophy. Clear? So, there you wanted to protect yourself so that the outside temperature and your body temperature do not intermix. Here what you want to do is, you want to have a sheet of layer on the structure which will allow easy conduction of the heat. So, heat dissipation has to be enhanced. So, design has to be dealing with the social aspects also, environmental aspects also, clear. Then comes the legal aspects. You remember my old discussion which I had with all of you. Then comes the technical issues, and once you have done this series of issues, then comes the financial issues. Now, the fact of the situation is that we are finding to handle physics much more difficult as compared to the chemistry. It is not easy to perform temperature control experiments in the laboratory at very high pressures. So, we are dealing with the pure physics right now, but it is extremely difficult that the chemistry, because chemistry happens at the molecular level slowly without telling you, you need not to take any efforts. Then the bio sciences or the life sciences, in the soil all these mechanisms are already occurring, you need not to do much. But when you deal with 25 MPa pressure, 35 MPa pressure, 2 degree temperature, the cost of experimentation is extremely high, and you have to take safety as a prime measure.